If you want to determine an empirical and molecular formula, that can be important, and definitely for chemists, because one of the ways that chemists get paid is, what is this formula, all right? And so we'll talk a little bit in this section now about percent composition. Now, percents in chemistry are usually percents by mass, which means how many grams are in something. So when you see a percent composition with a number next to it, in 100 grams, you'd have that many grams of the compound, stuff like that. As an example of what I mean by this, let's talk about ethanol, which is C2H6O. And ethanol is drinking alcohol. That's nothing you need to know, but it is kind of interesting. So ethanol has carbon, hydrogen, and oxygen. It has 2 carbons, 6 hydrogens, and 1 oxygen. But when you want to find the percent composition, it's 52.13% carbon, 13.15% hydrogen, and 34.72% oxygens. Now, a couple of things about this. First of all, notice that if you have the percentages of all the different elements in a compound, they should equal 100%, or by sig figs be pretty gosh darn close to 100%, if you know what I'm saying. Second thing is that a formula is a mole-based ratio. So in a formula, C2H6O, that's 2 moles of carbon for every 6 moles of hydrogen for every 1 mole of oxygen. It's not the mass values, like it's not 52.13 grams of carbon for a formula. We have 2 moles. So formulas are based on moles, and percentages are usually based on mass. And it would be nice to know how to go from a mass percent to a ratio formula, and it would be nice to know how to go from a mole-based formula back to a mass percent, and we'll talk about that in this section. So here's an example of how we can make this work. Let's say we have a 10-gram sample of a compound, and in the compound it has 2.5 grams of hydrogen and 7.5 grams of carbon. Let's find the percentage by mass for both hydrogen and carbon. And this may be kind of simple for some of you. If it is, I apologize, but I want to make sure we're all on the same page here, so let's talk about it. Well, percent by mass is always going to be the grams of what you're looking at divided by the total mass times 100%. So for hydrogen here, we have 2.5 grams of hydrogen, and there's 10 grams total. So 2.5 over 10 would be the ratio, if you will, of hydrogen to the compound. Let's multiply it by 100%. 25% hydrogen is found in this compound. And you can do the same thing for carbon. It would be the grams of carbon divided by the total grams of the compound. So in this case, 7.5 divided by 10 times 100, 75% carbon. And again, both of those percentages together should be about 100%, and they are obviously. Also notice that if you wanted to feel kind of lazy, if you had the 25% carbon, percent by carbon, start again. Also notice that if you had the first value and you were 25% hydrogen and you were feeling kind of lazy, you could have just taken 100% minus the percent hydrogen to find the percent carbon. So 100 minus 25% would give you 75% carbon, which is exactly what we found. So there's different ways to play these, and it's nice to know all the tools you have under your belt. Use the one that's best for you. If you know the formula, you can also find the percentages and all that kind of stuff too. And what you should do is first of all find the molar mass of the whole compound. So let's use water as an example to find the percent composition of oxygen and hydrogen in this case. So what I would do is first find the molar mass, and water is 18.02 grams per mole. So in the oxygen, there is 1 oxygen in H2O. So 1 oxygen on the periodic table is 16.00 grams per mole. If you look up the actual value in the periodic table, it probably has more sig figs, but to the hundredths place, that's 16.00 grams of oxygen in a mole. And we'll divide that by 18.02 grams of water in a mole. If you cut out the moles, it's just 16 grams of oxygen in 18.02 grams of water. Multiply it by 100%. 88.79% oxygen. Cool. Now for hydrogen, it's the same thing. You would take the two hydrogens because it's H2O, and to the hundredths, hydrogen is 1.01. So you'd have 2 times 1.01 to reflect the two hydrogens in H2O, but you'd still divide it by 18.02 grams per mole. That'll give you the percent of hydrogen, and the way I've done it there, it's 11.2%. Now notice if you wanted to get sig fig crazy on me, which is actually pretty cool, you could go 100 minus 88.79. 100% is an absolute definition. Don't have to worry about sig figs. Minus 88.79 would give you a better sig fig percent. It would come out to be 11.21%. So there's different ways of doing things, and you will get different numbers of sig figs. Think about that as you go through your values. But either way is fine. So again, if you want to find elemental composition from a formula, first find the molar mass, in this case 18.02, and then the grams of the oxygen go on top, divided by molar mass to find percent oxygen. And for hydrogen, it would be grams of the hydrogen. 2 times hydrogen would be 2 times 1.01, divided by molar mass times 100. Good to go. So here's a question you might see. What's the percent nitrogen in nitrogen monoxide? Now the molar mass of nitrogen monoxide is 30.01 grams per mole. That's a nitrogen plus a oxygen to get that number. So percent nitrogen, we would take the grams of N in NO. There's 1 N. Nitrogen on the periodic table, 14.01 grams per mole. We'd put that in the numerator. In the denominator, you'd put the molar mass, 30.01. So 14.01 divided by 30.01 times 100%. Put that in your calculator or just watch me answer it. Either way is fine. Anyway, it comes out to be answer B, 46.68%. So nitrogen monoxide is 46.68% nitrogen. And if you wanted to know percent oxygen, you could go 100 minus 46.68. I think that's answer D, 53.32, if I'm not mistaken. Anyway, this is how these things roll. Pretty chill if you want to go from one to the other. If you want to know an empirical formula from the masses of things, you can do that too. And the general idea is you want to first convert the element masses to moles, because in a formula, you're always going to have moles. You're not going to have grams. So you've got to turn grams into moles. Then you'll have moles of at least 2 different elements probably. So you'll take the bigger one and divide it by the smaller one. And that you're looking for whole numbers, all right? So if you end up with a whole number, you're good to go. Sometimes, though, you'll end up with weird fractions like 1.5, and you can't have 1.5 atoms, so you'll need to multiply by some integer to give the smallest whole number value. Now, I'm sure that's not the clearest, so let's look at an actual example. Let's say that we have a compound, and it's found to have 1.71 grams of carbon and 0.287 grams of hydrogen. Let's use that information to find the empirical formula. Well, again, in a formula, you have to have moles. So you've got to turn the grams of carbon into moles of carbon and the grams of hydrogen into moles of hydrogen. Carbon is about 12.01 grams per mole, so 1.17 grams divided by the molar mass, 0.142 moles of carbon. If you do the same thing for hydrogen, 0.287 divided by 1.008 grams per mole, that gets you 0.284 moles of hydrogen. And at this point, you do have like a rough formula. It would be C.142 H.284. But that's pretty ugly. All right, that's not a formula like we've talked about in class so far. So to get it into a whole number ratio, you divide both of these numbers by the smaller number. So 0.142 is smaller than 0.284. So you'll divide both of those numbers by 0.142. 0.142 divided by 0.142 is, of course, 1, so that's nice. And 0.284 divided by 0.142 is a ratio of 2. So we have 1 carbon, 2 hydrogens. The empirical formula of this molecule, CH2, and that's kind of cool. Now, it's not the final molecular formula. We'll talk about that in a little bit. But if you have the masses, you can easily find the empirical formula, grams to moles. Compare them. If you need to multiply by something, empirical formula. Now here's another example with chlorine and oxygen. So we've got so many grams of Cl, so many grams of oxygen. Let's find the empirical formula. So like before, grams to moles is the first thing for both chlorine and oxygen. So chlorine, if you do this, chlorine is 35.45. So 5.31 divided by 35.45 gets you 0.150 moles of chlorine. And this would be a good thing to practice to make sure you can get this. I'm going to start kind of cheesing over some of the details because I want you to be able to do this yourself. And likewise for oxygen, 8.40 divided by 16.00, that'll get you 0.525 moles of oxygen. So see if you can do this yourself. Make sure you're good. But what this means then is you have 0.150 moles of Cl for every 0.525 moles of oxygen. Now that's an ugly ratio once again. So we'll divide both of those numbers by the smallest number, which is 0.150. So 0.150 divided by itself is 1, no problem. But oxygen here, we get 0.525 divided by 0.150, and that comes out to be almost exactly 3.5. So what this is telling you is that for every 1 chlorine, you have 3.5 oxygens, but you can't have a half oxygen molecule. That just doesn't roll in chemistry. You can only have whole numbers. So what you could do in this case is multiply the 1 and the 3.5 by 2. Having a whole number, super important in chemistry when it comes to formulas. So instead of having 1 to 3.5, multiply both of them by 2. It's like taking that whole formula and taking it twice. If you do that, you get Cl2O7, and those are whole numbers. Chemists can deal with that, all right? You can find molar masses, blah, blah, blah. So for this molecule, the empirical formula is Cl2O7. So if you see one of these weird fractions, just think about multiplying everything by a whole number. Good to go. So here's kind of the general idea of what you want to do. And with that last example with Cl and O, that's exactly what I did. We started on the far left with grams of Cl and grams of O. We then divided by the molar mass to get moles of Cl and moles of O. And that was an ugly formula, but what you want to do then is divide both of them by the smallest number. So we divided them both by 0.150 to get a 3.50 to 1 mole chlorine ratio. And that's better, but we want to have whole numbers, so we multiplied both of those by 2 to get Cl2O7, the empirical formula in that plan. And if you can follow this, you absolutely have this process down. It's not too hard, it takes a little bit of practice, but it's nothing you can't do. And if you get stuck or anything, you let me know, or let the Learning Success/Avid Center people know too. We're all here to help you. We will definitely make sure you got this nailed down. So here's another example. And this example, though, we're going to start with percentages, mass percentages, and we're going to turn that into an empirical formula. So in the last example, we had grams of oxygen and grams of chlorine. We turned them into the empirical formula. In this kind of problem, we have percentages, and we're going to turn percentages into an empirical formula. And the only real difference is that if you have percentages, you want to assume you have a 100-gram sample. So that way the percentages become grams. You can then take the grams, turn them into moles by dividing by the molar mass. You'll get 2 mole amounts. You'll divide the smaller by both of them to try and get at least the first one a whole number, and the second one will hopefully be a whole number. But if it's not, you can multiply everything through to get whole number atoms, because remember, chemists like whole number atoms. So in this example, we're going to look at some kind of a bacterial fermentation of grain, and we end up with a gas which is 27.29% carbon and 72.71% oxygen. And the question is, what's the empirical formula of this gas? So again, the general idea will be assume 100 grams, grams to moles, compare the moles, multiply by some kind of number if we have to get whole numbers. Good to go. In this problem, if you assume 100 grams, that would be 27.29 grams of carbon and 72.71 grams of oxygen. So that's why I like 100 grams. Yes, you can use 1 gram. You'd have 0.2729 grams of C and 0.7271 grams of O, but I don't usually think that way. The easier, the better for me, but you could do that if you want to. It's no problem. So in my version, 100 grams total, 27.29 grams, 72.71 grams of O, good to go. So when you turn the grams to moles, 27.29 grams of C divided by 12.01 grams per mole gives you 2.272 moles of carbon, and 72.71 grams of oxygen divided by the molar mass of O, 4.544 moles of oxygen. So at this point, you have a formula. It's C 2.272, O 4.544, but that's really messy. Divide both of those numbers by the smaller number, which in this case is the 2.272 number. When you do that, 2.272 divided by itself is 1, 4.544 divided by 2.272 is 2, empirical formula CO2. So this is carbon dioxide, which has been created. So this is the idea with percentages. Percentages assume 100 grams to grams, grams to moles, compare the moles. Good to go.